Hey guys, this is Unit 5, Lesson 3. Today we're going to be talking about another type of transformation called vertical stretches and compressions. So the way you can recognize these is when k, our variable, is multiplied by the function. As you can see here it says vertical stretches and squishes. It's another word for compression. And then we have k times f of x, or our function. It also might be written without the dot, so k times f of x. And this affects our outputs, or y values. So again, we're going to be putting in the same inputs and getting different outputs. Now this first example is a stretch, and you can tell it's a stretch because k is going to be greater than 1. And we say the graph stretches by a factor of k. So this example, we're using the graph of the cube root of x, and then it's going to be stretched by a factor of 2. And the way we're going to sort of work this out, or the way I'm going to prove it to you, I guess, is by using an input-output table, like we did with our vertical shifts as well. So I'm going to draw a little output table. And at the top I'll put x, which is our input, and then f of x, which we know in this case is the cube root of x, and then our stretch, which is 2 times f of x. And then I'm going to choose 3 x values, or input values, that I can see on my graph, and also that I know the answer to, so I don't have to use a calculator or anything. So I'm choosing -1, 0, and 1, because I can easily solve that for the cube root of, I can easily solve for the cube root of these values. So I know the cube root of -1 is -1, cube root of 0 is 0, and the cube root of 1 is 1. And then over on the far column I have my stretch, so I just multiplied 2 times f of x, -1 times 2 is -2, and so on. And I'm going to plot these points over on my graph, just to show you guys that for our f of x graph, I'm going to plot -1, -1, 0, 0, and 1, 1. And if I connect those points, I'll get my f of x graph. And I'm going to do the same for my stretch, 2 times f of x, and I get -1, -2, 0, 0, and 1, 2. Connecting those, I get my 2 times f of x graph. Our next example is of a squish or a compression, which you can recognize when k is between 0 and 1. And if you think about that logically, it's just sort of like if you multiply a percentage or a fraction by a number, it makes it smaller, right? So we're going to say that the effect that has on our function is to squish the graph. And the example graph we're using here is sine of x. Not sure if you guys have worked with sine yet, but it's basically this wave-shaped graph. But not super important that you're familiar with this kind of function. The example will still be relevant and easy to understand. So really quickly here, again, I'm drawing my input-output table. And up at the top I have x, my input, and then my output for f of x, which in this case is sine of x, and then my compression, or my squish, which is 1/4 times f of x. And again here I'm going to select input values that I'm familiar with. So I know you guys aren't familiar with sine, but an easy one here is going to be -pi/2, 0, and then pi/2. And I know that for those input values, that is where the graph is going to hit -1, 0, and 1. So that's going to be really easy to work with as we do our compression over here. So multiplying multiplying 1/4 times -1, I get -1/4. 1/4 times 0 is 0, and 1 times 1/4 is 1/4. And then I'm going to plot those on the graphs over here. So -pi/2, 1, 0, 0, and pi/2, 1, connecting those for our original graph. And then we have -pi/2, -1/4, 0, 0, and pi/2, 1/4 for our squished graph. Now let's go through our lesson objectives. Can we recognize a vertical stretch and compression transformation from the symbols k times f of x? I believe we can. We also learned how to determine whether a function will stretch or compress. And we know that if k is greater than 1, our graph is going to stretch out, right? Multiplying something by a number bigger than 1 makes for bigger numbers. Something between 0 and 1, the graph is going to squish. And then we know how to create an input-output table for these stretch and compression transformations. And we know how to plot the points to check. Good job, you guys. Yay.